Good evening. Welcome to HKISC YMG. And since we founded YMG, it's always our mission to find these very short but unique technical seminars, and we make sure it's free. So today it's our honor to have two engineers from Bureau Happel International Hong Kong, which is a company specialized in large-scale steel structure design. So first we have Daniel Wood, Associate Director from Bureau Happel, who's an expert of architectural engineering design, and we have Emilio. Emilio is an expert of parametric design. Today they're going to use their project, City of Dream in Macau, to illustrate how Bureau Happel adopted this parametric design in engineering design process. So everybody, please join me to welcome Daniel and Emilio.
Use the microphones. Can you hear okay in the back? Is it loud enough or should we use the microphones? Okay? A little bit louder? A bit louder. Okay. So thank you for the introduction, Rogan. It's very nice to be here. This is a project that Media and I have been involved with for at least the past 2 years. We with more of a general view. Media has been specialising in the connections design, grassland scripting, analysis of the steelwork connections. And so, as you probably know from the flyer, today is talking about the project in general, focus specifically on the connections design, the steelwork connections design, how we designed, detailed and documented those connections in a very short period, from 9 months in total. And that was using a bit of software called Grasshopper. So Amelia is a bit of an expert in Grasshopper. I'm going to start by going through items 1 and 2. So I'll give you an overview of the project, what the project is, where it is, what it's about, what it looks like, what the structural aspects of the project are. And then going to start focusing on the exoskeleton and the connections in particular. Emilio is then going to pick up and spend around 45 minutes looking at the detail of what we actually did, how we designed the connections, the software we used, the scripts, the methods, how it looked in the end. And there are two aspects to that. One is the detail aspect, so it's going to look at what we did on this project. There's also going to spend around 5 or 10 minutes introducing general Grasshopper examples. So some of you will be familiar with Grasshopper, you know what it does, how to use it. Some of you might not. So to aid your understanding of the detailed parts and the more complex parts, Emilio has a very simple example of using Grasshopper just to introduce you to the software. And then at the end I'll come back and give you a summary of the overall project and where we are outside. So here's the background then. So I'm sure you all know where Macau is, 1 hour ferry trip to Macau. This is a go-to script where the majority of the gaming, casinos and the resort facilities are. This is the City of Dreams complex. It was completed in 2009. And on the City of Dreams you've got the Hard Rock Hotel, which you may know, Crown Towers, Grand Hyatt, 2 towers there, as well as the retail, gaming and the casinos, the ground floor, the podium area. So this area here, so highlighted in yellow, this is our site. So the client, Milko Crown Entertainments, they had a design for a 40-story building on this site. They started the construction, and in 2007, 2008, they stopped. So they installed the piles, installed the foundations, and stopped work. So this is how it looked when we started working on this project in around 2012. So in 2012, the client, Milko Crown, appointed a new design team. So they had a brief to design a 42-story, 6-star hotel in Macau. And they wanted it to be eye-catching, iconic, outstanding. And so they employed Zaha Hadid as the architects. The building on this campus, the Innovation Tower, which is also a Zaha Hadid building. So you must be familiar with their architecture. Bureau Happel were the structural engineers, the facade engineers. We also had a role for the concept MEP design at the beginning. And we had 2 offices involved. So our London office was working hand in hand with Zaha Hadid in London, and our Hong Kong office as well, working with the local team. So we have Lee in Orange, local architects, GRP, MEP engineers, and WGP cost consultants. So that's how the project came about. So we're going to start off with the architectural response. So as always, the architect starts to look at the massive diagrams and the overall look at the building, how it's going to look, what's the shape, plot ratios, this kind of thing. And then they start thinking about the program distribution, so let's face it, when a client employs how it is design a building, they want to see these kind of things, the architectural renderings, the images. This is going to be over $7 million US, so they want something that's going to be outstanding, that's going to put their name on the back of the account. So this is what Zahari came up with. The entrance experience, so this is as you go into the entrance on the north side of the Institute Dreams complex. This is the atrium, so as you go into the hotel, to check into the hotel, you've got a great big 6-story atrium, which includes these 6 seating places on each side of the atrium. This is where you check into the hotel. You can see if you look to your rooms, you've got a great view of this fantastic space. The restaurant floor, so number 21, 23, the Hamlet restaurant floors there, including private dining. You can see this great big exoskeleton structure and the massage room over the top. So Zahari did their job. They came up with something really iconic, a signature building that's going to put Institute Dreams on the map of the ground. The gaming rooms, of course, because this all has to be paid for somehow. And then there's the 2-story suite at the top of the hotel for the big rollers. The rooftop swimming pool, of course. And then this is how it looks tonight. Now this is a very short clip from a video that you can find on YouTube. So if you go on YouTube and type in Zahari Institute Dreams, there's a 4-minute video. So this is just a small clip from the video, but it would be worth looking at. It's quite a good video. You get a striking presentation within the 1 hour limit, so we couldn't display too many videos. But it gives you a feel for the overall mass and the size of the building, how it looks. It's really quite spectacular. So there's the background. You've got a feeling for what the what it looks like. And this is the structure that we come from. So to start with, there are a number of aspects. This is a shot, a screenshot from our Revit model. So everything is documented in the Revit model. So the general arrangements, the framing plans, the details report, and that was in conjunction with our level. So models of this and their aspects. And we had other models in Hong Kong that we come from. And these are the component parts. So there's the exoskeleton structure. So this is a true structural exoskeleton. This is not an architectural appendage that is just on there to look pretty. Very early on we decided that this would be an exoskeleton structure. There are no columns hidden behind the facade supporting the building. So that's the exoskeleton. Floor slabs, obviously. There are 2 reinforced concrete cores. And a series of internal columns. This is what it looks like when you strip back the steelwork from the composite floor. So this is the 2 cores that contribute to the lateral stability as well as providing vertical support to the tower. This is a cutaway that just illustrates some of the key components. So this is part of one of the reinforced concrete cores. We have composite beams and composite slabs which form the floors to the hotel. There are a row of internal columns that run around the 2 cores. And so this space here would typically be a hotel room. The space behind it is the corridor, so that's the guest circulation. Outside of that, this is the only vertical structure. So the exoskeleton supports the floors at this point, no columns there. And you can just about see there some small stuff. So we have to connect the internal spaces with the exoskeleton. And this is the job of the stuff. The arrows facilitating the false paths that the exoskeleton. The stability of the building is provided by both the reinforced concrete cores and the exoskeleton acting together. So the active composite is the excitement walls and the windows. Remember in Macau we worked into 200 G a week, 200 G a year in terms of good windows. It's quite a high lateral resist. So this is now an introduction to the exoskeleton. So as I said, we're going to gradually focus in on the exoskeleton and then on the connections of the levels before the video shows you how we design those. This is an architectural slide and it's showing the architectural envelope and it's split into different areas. So the blue area here shows the flat sided element. So this is the architectural facade envelope. So these blue areas are completely flat, planar sides of the exoskeleton. The green and the purple are the transition areas where we go from flat sided areas to more complex doubly filled areas, the central section. You might hear us referring to the central section. This is the part here. And so remember, as I said, these are the architectural facade surfaces, not necessarily the structural components. This is how it looks when you look close on the exoskeleton. So you can see there's the exoskeleton here. So the exoskeleton are obviously structural steel members, but they are clad in aluminium. So it's an aluminium box that fills around the steel. Behind that, you've got the facade, so a unitized curtain wall system, and then behind that, floor beams and floor slabs. This is an exploded axonometric, so just makes it all a bit clearer. So you can see the floor structure behind, no columns, no vertical structure there. The facade line here, some holes here which allow the studs to push through. So these are obviously critical elements. So these allow the load to be transferred from the floors out through the stud and onto the exoskeleton. And you can see from these views the aluminium cladding around the exoskeleton, the steel work, which is the exoskeleton, the stud, the side here, the floor structure behind. And this is how it all fits together. This is the anatomy of the exoskeleton. In the central section, it all gets a bit more complicated, but actually it's the same system. It's an exoskeleton on the outside, facade, floor structure on the inside. So the same system, just a bit more complex in terms of the geometry. This is an extract from the structural model. So when you strip away the concrete, as I said, we're focusing on the exoskeleton and the connections. So strip away the concrete and the floors. So this is what you're left with. This is the exoskeleton structure on its own. This is the same view again. We've coloured them up to show the different section sizes. So it's just giving you an illustration of how complex this was. So there's a range of steel grades. At the bottom of the building we use an S460, but the lowest one height to keep the section sizes small. SD55, SD55 elsewhere. A mix of section sizes. So I said the different colours on this image represent the different section sizes. So it's quite a mix of section sizes. That helps us to keep the tonnage of steel there. So it's a balance between the complexity of lots of sections and keeping the weight. Planar and single curvature. So you may remember when I was showing you the architectural facade envelope, I talked about double curved elements. That's the architectural envelope. But structurally, we get to planar and single curved elements, which I'll explain in a moment. And a mix of open sections and tubular sections, again, also the structural efficiency of the steel elements and keeping the weight down. So now onto the exoskeleton connections, again, as I said, focusing more on the main points of the topic for tonight's talk. So this is showing you how the planning comes together. So the steel work for the exoskeleton is surrounded by the pipe section, brackets that allow you to connect the aluminium cladding onto the steel work. And so, as I mentioned, the architectural envelope, it's all sorts of funny geometry that's following. The geometry from Zaha, it's double curve, twist and block, whatever they wanted to do. And the structure inside, we then have two choices for the structure inside. We can follow slavishly the architectural geometry, but that's going to result in something like this twisted, warped, doubly curved members. The only advantage of that is that the brackets connect the steelwork and the aluminium are going to be a constant size. It's the only advantage. The steelwork is going to be tremendously complicated to fabricate, very expensive, time consuming. The choice we made was to use single curved elements. So we took the architectural envelope, we used our software to draw the structural elements through there without popping out of the planning. And then we found a far simpler structural solution. This is far easier to fabricate, cheaper, it's going to be leak tolerance a lot more than a twisted element is. The only disadvantage is that these brackets have varied dimensions. But really, this is about putting the complexity where it's best controlled. So facade contractors, facade designers are very capable of dealing with complexities of having brackets at different lengths. So we keep the steelwork as simple as we can. Facade contractor.
Cannot hear, sorry.
You can't hear? Okay.
Can't hear. The technical part is
So I'll use the mic. Is that better? Can you try and find a microphone that works?
Testing 1, 2.
Okay, so you can hear now, yeah?
okay.
Okay. Right, okay, so we've kept the complexity where it's best handled. The steelwork is relatively simple. We have single curvature steelwork. And when you put those elements together, so this is an extract from
an image that we've made in Rhino, the drawing software. This is without thinking about how the connection looks, to just putting those members on top of each other and just looking how it looks at the connection. So our challenge in terms of the connection design was to think how to connect those members together and to get the extremely large forces through the connection. And this is just an idea of how the connection would look. This is a very early concept scheme design image, so it doesn't necessarily look quite like that now, but it gives you an idea of what we were doing. And as the members come in, you can see from this shot and this one just about, as the members come into the connection, they're not square with the connection. And that's just a result of keeping the members as a single curvature. So it keeps the member simple, and then we deal with it at the connection by picking them up together. And just to illustrate the point, so this is, again, this is a small part of the central section. This is a steelwork. This is drawn in Rhino, Rhino software. And in that software, you have the ability to analyze the geometry. So this is where we've taken a look at the Gaussian curvature of the geometry. And basically what that means is everything's green here, and you can see from the scale on the left that that means the Gaussian curvature is 0. And this is just a screenshot that I took from Wikipedia to illustrate the point. If you have a positive Gaussian curvature, that indicates you have a doubly curved surface, something like a sphere. Negative, then you have a saddle shape, but it's double curved all the same. And 0 tells you have something which is single curvature. Another thing you can do in Rhino is analyze the radius of curvature. So this is useful just to get a feeling for how easy the sections will be to fabricate. So you can see here we have a range from 4 meters of radius to 85 meters radius. So again, it gives you a feeling for how tight the radius is on the steelwork. Obviously, fabricators can curve steelwork to a certain radius. The thicker the steelwork is, then the larger the radius. It takes more effort to bend the steelwork. And at this point, a lot of the images I've been shown have been from the concept and scheme design stage. At that stage, we weren't appointed to do the connections design. It was envisaged at that point that the fabricator and the contractor would design the connections. Nevertheless, we had given some thought to how we thought they would go together. And so this next series of images just give you an idea of what our thoughts were at concept scheme design stage in terms of how the connections would look. They're all on the flat-sided exoskeleton, so it's the easy part, or the relatively easy part. But it gives you a feeling for the scale as well. So you can see this is a hotel floor-to-floor height. And you can see to get the connections to where you have some pretty large pieces of steelwork. This is almost a story height in this case. And again, another view of that. So this is, as I said, hopefully a very brief introduction to the project, the background, the exoskeleton, and the connections. So I'm going to hand over to Emilio now. So he's the guy who did all the hard work and the clever work, and he's going to tell you what he did using Grasshopper to design and document these connections.
Thanks, Dan. Terrence, come on down. Yeah, so as Dan just said, by the way, if I get too loud with the microphone, just let me know. That might be the other issue with me. I'll block your view. So the challenge. As Dan's told you, this is a complicated building, and complicated buildings generally require complicated solutions. And he's given you a little bit about the geometry of the skeleton, about what happens at where the members connect. But what is really the challenge when you say, give me detailed connection designs for a building like this? Usually this type of thing is not done. In structural engineering, usually this goes to a subcontractor of the contractor. They do the design. But as you'll see, as we go through these 4 steps that we have to do, this is all atypical work, and extraordinary work with an extraordinary program, which is why this is a very special example of how to use Grasshopper. So we've got 4 things to do here. Determine unique connections, meet a bunch of constraints, analyze the connections, and document the connections. And as you'll see, this all involves extremely difficult things that are not normally seen. What does that mean? Well, first of all, as engineers, we look at this and we say, what do we have to do? We have to design, right? We have to make sure this thing stands up. But as you'll see, there's a lot that goes into that on this project. It's not a code method type of thing. In fact, as you'll see, even doing hand methods isn't something that you're going to end up doing. You have extremely complicated stress states with the complex geometry, which means that you got to go and do 400 finite element analysis models, okay? And that's already in and of itself very hard to do. But when you say, well, since it's a connection design, we have to do this interesting force mapping procedure, which involves dealing with 57 million lines of data, you start to know right away as an engineer that this is not your average job, okay? But it gets worse because we have to consider a lot of other things. On this job, you're working with an A-class architect, which means you have A-class architectural constraints. Now, with these amazing intersections that we just saw, we're going to have connections that are very complicated. And they need to fit within a very aggressive, complex envelope that comes from Zaha, okay? We also have fabrication constraints, okay? Because whatever we make has to be able to be built, all right? We want to find similar nodes and be able to make the simplest possible connection for the fabricator. And that's not easy to do when you're dealing with 460 API grade plate, okay? That's going together in a very funny fashion that is not normally found, okay? And you got to document all that. You with me? Okay? One more thing, and as we all know, whether you're a student in this room or a professional, the biggest thing you have in life to constrain you is time. Okay? We could do this if it took 10 years, it would be nice, but we have 9 months after we develop our tools, which practically speaking for the everyday engineer means you have about 4 hours every day to complete a full detailed design of this connection. Yeah, that's where we're operating right now. That's the challenge in a nutshell. That's what we have to do. Let's go into each one of these individually because they each merit their own little talk. First things first, finding similar connections. Why do we do this? On a normal job you do this, but on this job it's especially important because remember, time is of the essence. If we can make a connection work in 10 places instead of just 1, we have just de facto sort of divided our work by 10. But it's not just us, it's also the contractor, okay? But it's not that easy to do considering the only thing I have geometrically to start with is this Rhino centerline model, okay? And these section sizes that are on the layers for this geometry, okay? So basically, we need to be able to determine not only will the members connect in the same manner, okay, same orientation, but also will all those members have the same sections, because only then can you have the same detail. Not so readily available, and considering what Dan said before, where we have different sections being used everywhere because of complex loadings and trying to keep the weight down, you know, it's not readily available for us. How do you get past that? This is a critical step. It divides the work by a factor of 10, potentially. Okay, meeting constraints. Like I said, we have a lot of constraints in this job that you don't normally see. First things first is you have this, what you see on the screen right here is this crazy envelope that you must remain inside of for the structure. This came from Zaha Hadid, and just to give you a little bit of an idea, so this is it zoomed out. Remember what Dan showed you, okay? Here's what you have up close and personal. This is to scale. This is what you would look like standing out there in space, and if you were red, okay? And this is what my connection is going to look like inside of it, right? So essentially, that's the weird, crazy geometry that you have to stay within. And if you stick out the size of this bottle cap out of that envelope, you're going to get an email from Zaha saying you didn't deliver what you promised to. So just imagine that. You've got to stay within that, all right? We're dealing in 3D world here. And with a 3D world, you have to deal with 3D. Your solution's got to be 3D. So not only you got to be able to say, what's that connection going to look like logistically, but you got to be able to say, okay, it fits within the architectural envelope. And now what am I going to do? I got to be able to justify in 3D world that this thing can go together. There's actually, you have to be able to say, this for sure can be put together. The contractor can't come back, give a claim that said you actually didn't do your job either, okay? This is all coming on the front end of things. And then when you sit there and you say, okay, I've got past the first 2 big hurdles, remember what I said, we're engineers. We're actually on this job to do another thing, which is determine what this thing should look like, but also what the plate thicknesses should be. When you got complex stress states like this, and notice the huge forces and the orientations of these forces, your prototyping is going to get you to this point, all right? I want you to remember this point. This is what you get to before you even get to the analysis stage. This is what you've done already, okay? And then you get to the fun part. This is the part that we as engineers love, right? And some people laugh. They don't like it, right? So basically, finite element analysis. Why is it not normally done on a connection job? Well, because you got code methods that usually take care of everything for you, or you can do it by hand. But as I said before, we have something called a complex stress state right now. And I'm going to get into what that means right now because it's critical for us in the room to understand what that is. Essentially, on the left is something that you would normally see, all right? Now, let's assume that on the right is what we'd see on COD, even though we know, in general, like the geometry is not that nice. Let's just focus on the forces here. As you can see on the left here, in general, you're able to use simplified connections that only will transfer shear or axial forces, all right? We know very well that this is only going to produce maybe 2 degrees of freedom worth of forces onto our column. But on COD, we don't have that luxury because every one of the members is so big, carrying such huge forces to be efficient, that essentially you can't have an analytical pin be put here. It has to be fully welded, which means that it's going to transmit 6 degrees of freedom worth of force into your plate right here. What does that mean? It means you're playing in the complex stress state of things, okay? And if you guys have ever played with von Mises stress states in a finite element package, this is what we're talking about. It's a nonlinear failure envelope, and I think the best way, it was explained to me this way, the best way to understand this is if you had this cross member here, right? And we take the vertical member and we decide to put that into compression, we know right away that we're talking, oh, these arrows are drawn the wrong way. We know right away that this is in compression. Ignore the arrows. If we put this in tension, we're adding to the stress state here. Now when this goes into compression, this also goes into tension because of Poisson's ratio, as we know. When you put this into tension, you exacerbate that problem. You exacerbate that problem so much so that if you put both of these at yield, this is about, in this purple zone here, about twice yield. And by the way, this is a planar example, very easy. When you got 6 degrees of freedom, you're dealing with this problem right here. And I don't think you want to be doing that by hand, especially because you can't do it by hand with envelope solutions, because it ends up being grossly over-designed. The only way forward is creating a nice, pretty stress plot like this, okay? Now, what is this? This is from Robot. So essentially, Robot's done all the nice calculations for us and given us the von Mises stress. But the first thing you need to do before you can jump into that is create one of these. And like I was saying before, this has a lot of time involvement in it. I mean, this is why it's typically not done, because if it was easy, it's actually, you know, most people would do it. But here we are, and we have all these things, and I don't want to underestimate everything, but the one thing I want to focus on is this one right here. The mapping of the forces is an exercise that we had to do on this job that most engineers will never see in their career, because it's generally not needed. But you need to be able to take the 57 million lines of data from this Midas model, which is where everything was modeled. You need to be able to do, if you had your matrix analysis of structures, you need to be able to do crazy stuff like this to it, and be able to put it into Robot successfully every time, twice a day. Okay? This is not an easy job, and it needed to be done at that kind of pace with that kind of a surety, because essentially, this won't stand up unless you calculate it right. This is just a pretty picture right now, okay? It doesn't meet the structural constraints. Now, I want to point out this plate right here. Sort of keep that in your mind when I go to the next slide, because in the real world, when you have some guaylo standing in front of the plates in the shop in Guangzhou, this is what it looks like, okay? Look how big this is. 120 thick plate, 460 grade API. This is big stuff. Once you actually consider the complex stress state, this is what happens. You need to have this because at the end of the day, the building's integrity relies on it. Obviously, someone is very impressed with the floor node that goes behind it. This is the size of things that we're talking about that I just showed you right here. This is what it ends up looking like in real life. And we're going to get to a little bit more in this presentation, real life. I was in Macau on Sunday. It looks great. She's looking down on us now, the mega node. Okay, finally, documentation. After you do all of this, everybody's got to be on the same page. You've got to communicate your work to the rest of the team. We're using Rhino. Most 2D drafting is done in AutoCAD, and the contractor's using TechLab. So how do we handle all these softwares? Especially when you consider, I need to be able to describe shapes like this to the contractor. In typical ways, just for the students in the room, you might just say, well, I'm going to start taking a bunch of section cuts, a bunch of different 2D drawings, putting on coordinates and having a bunch of schedules of coordinates. The problem with that goes back to, once again, the main constraint, time. That could easily take a day in and of itself for each one of these connections. And remember, we just don't have that luxury. So once again, you have to get innovative. We have to sit there right away, and we recognize from start to finish, we have 4 main tasks that need to be done, and each of those has some severely unique challenges that need to be addressed. And how do we do it? Well, you probably know because it's on the poster, but we use Grasshopper. And essentially, this is a cool project because you don't normally see Grasshopper being used in such a visual manner in this way for connections design. And it was the only way for it, as you'll see, because we had to get innovative. Now, what did we use Grasshopper as? the one thing I want to stress as we go through this next part about Grasshopper is Grasshopper was not a black box tool. Okay, now what is black box? Okay, black box programming, because at the end of the day, this is what we're doing now. We're programming. All right, black box programming, I can explain to all of you because I know all of you are inherently programmers, because everybody in this room has used Excel. Have you ever had an Excel sheet where you basically made some huge Excel sheet, and by the end of it you didn't know how it worked? You threw it in, yeah, someone's laughing. You put in an input and it comes out an output and you go, well, it doesn't really make sense, but at the end of the day, that's all I got. That's a black box, okay? And as you'll see as we go through this, we do not have this situation here. We are using Grasshopper, in fact, as the go-between sort of BIM modeling tool that is also parametric between all these different softwares, as you'll see, okay? So what I want to do is I'll just show you real quick what the capabilities of this script is. And as you look at this right now, if you're not familiar with Grasshopper, you're probably thinking, this looks like spaghetti and batteries. That's okay, we'll get into that. We'll get into what these things are. This is a script, just like you've seen in the Matrix or something like that. This is just a computer code here, okay, that we made. But like I said, on the tone of being visual, here's a real quick video of our script in action. And I'm not going to explain it at all, just notice how much visualization is possible. I'm doing things behind the scenes here with Grasshopper to instantly show things. This is live time, by the way. This one is not sped up. The rest of my videos are sped up about 25 to 50%, okay? So everything we're showing here today is done in real human timescales, which is why we're able to get stuff like this done, and all the connections, the 2,500 connections that we need to do, we got those out on time. It's because of live streaming data, okay? At the end of the day, we can create really cool models like this, all right? So, what do we want to do here tonight? As Dan said, I want to step away because I know we have students in the audience and maybe some Grasshopper people, Grasshopper enthusiasts, and different varying levels of people in Grasshopper. Let's take a step back and describe what Grasshopper is, okay? And then do a quick tutorial on that, and then we're going to go back to COD to be able to describe to you exactly how we utilize that to solve those 4 challenges. What is Grasshopper? Grasshopper is a plugin for Rhino, okay? You can get it for free, and as long as you have Rhino, you can use it. I'm going to boil it down to 2 points here to take away what it is. It's a parametric design tool. What is a parametric design tool, media? Well, what this means is you're going to create something in a program that essentially have a bunch of parameters, just like any other time. But as Grasshopper, as you'll see, allows you to change those parameters extremely rapidly, thereby changing the whole system rapidly. It's also visual programming, and you might not know what that is, and you might not be a programmer, but I know, as an American, it's fascinating to be in a country like this where people are born with 3 languages under their belt. Who speaks more than 3 languages here? Okay, 2. Most people in this room are speaking 2 languages. You guys are just being shy. So I guarantee you one thing. If you come back to me and say, Medio, visual programming was not the easiest language that I ever learned, okay, and I know a lot of you speak Mandarin, then I'll buy you dinner, okay? Because this is the easiest programming language you're going to get, all right? And I want you to remember this little equation that I made up. It's not actually real. Programming equals geometry, and geometry equals programming. Remember this as we go forward, okay? This is very important in Grasshopper, to remember that everything you're doing, you're programming, but you're also creating geometry. You're going to see that here. So, who uses Grasshopper? I would like a show of hands. I didn't get a lot. I know everybody in this room is at least bilingual, so can I get a show of hands of who uses Grasshopper in the room? Christoph, Herr Kommissar, and Rojam, yeah. Anybody else? Oh, sorry, yeah. Oh, yeah. All right. So we got actually not too many people are using it in this room, which is great. I'm glad we started with the easy example. It's not just us in this room in the building services industry who are using Grasshopper right now. A lot of different people are using this software, and I think as we'll go forward in time, we'll see a lot more people using it. When I was living in Dubai and working for Bureau Happold out there, I met a jeweler who was doing really cool things with Grasshopper, who was doing 3D printing Grasshopper. And that's the thing, is manufacturers are getting a lot more involved in this. This was one of the students in the room, one of my first homework problems in a fabrication class in grad school. Used Grasshopper, dabbled in that, and fell in love with it. And here we are 3 years later, and we're still playing with sliders. So this is the stuff that's all possible. The goals for the next little bit here is simple. I want to foster excitement amongst especially the students here about what to do with Grasshopper and how cool of a tool it is. I don't want you to think that you're going to walk out of the room being an expert or even knowing how to use it, but just think, keep your mind open to what it can do for you. And that's why first, like I said, we're going to do the introduction and then we're going to go back to COD. And the key for the day really is just keep your mind open, don't try and scribble things down, and think about how you can use what I'm showing you on the screen for your thesis or for your project. Keep your mind open to that. Remember, as we go forward here, programming equals geometry and geometry equals programming. So, the first thing we're going to do, quick example, and it's called the parametric arc example. We're going to create a 3-point arc that's parametric, which means that it can be moved easily, its radius can change in 2 different ways very easily. You're going to see what that means in a second. So, here we go. Grasshopper screen on the right, this is Grasshopper land. Rhino screen on the left, this is Rhino land. Programming, geometry. But remember, those 2 things are synonymous, okay? So this is also geometry. This isn't really programming, but the results of the programming end up here, okay? So I just created one of your batteries, what we call components, and this hosts a point. We can create a geometry in the programmatic world, or we can create it over here. And what you're seeing is I just created it in the geometry world, and I referenced it into the programmatic world, as can be seen as it turns red and green as I click it. So now it exists. We have a point that exists over in parametric world, and we're going to start playing with it parametrically. So remember, our end game is to start manipulating geometry. That's what this tool is all about. So if this was CAD world, we all know how to use CAD. If we wanted to play in CAD, how would we, let's say, move this point? We'd type in move, we'd type in a vector, and we'd point to the vector, we'd snap to something, whatever. But in this new world that we're dealing in, we're dealing with more batteries. We're dealing with a move component, okay? So basically, this point is an input. It's geometry. It's asking for the exact same things, geometry and translation vector, as you can see here. So I'm going to give it that. Because Grasshopper is a visual tool that also has geometry components, it already has an X vector involved in it. I will type in an X vector, and what you'll see next is pretty cool. We're going to create our first parametric point, right there. And I shouldn't say parametric point, because actually this isn't parametric yet. It really, we can't change it easily. That's just definition of what is parametric. It's programmatic point. This does not exist yet in Rhino. It only exists in Grasshopper, but it can be previewed in Rhino. So just remember, Grasshopper is a sort of, Rhino is a preview window to Grasshopper. We have 2 points now, and what you're about to witness is your first parameter, and it's called a slider, and I still think sliders are cool, okay? And essentially the slider is the epitome of what it means to be able to quickly change your entire system based on the one parameter. Remember, you choose the parameters, you choose the system, you know what you're trying to model. It all comes down to having the medium to allow you to rapidly prototype things and also to be able to, you know, just see things visually with your mind. Right about now, we've got our slider here, and you're about to see for the first time, watch this point. It disappears. Where did it go? What do we do with it? We'll find it. There it is. Now watch and do ooh and ah. Ooh. Ah. It's pretty cool, right? Now, what am I doing here? What am I actually doing? I'm going to pull up this yellow panel over here to show you. All I'm doing is I have a unit X vector here, and I'm just playing with that. So if you see this, it's just changing it. But do I really care what the vector's magnitude is right about now? No, I'm doing a visual tool. And I don't need the program. If this was Excel, I need the program to tell me a number, to tell me what's going on. But I don't need that in Grasshopper. I have a nice little screen over here that shows me that live. I can play with it with my hand, and I can use my eyes. Remember that, that's key. It's an extension of your hand. You are now just visualizing things way easier than you could with any other medium. So remember, we have now 2 points to find. And what are 2 points? Put a line between them, right? In CAD world, you can snap to them. You turn on your own snaps, you go 1, 2, you have a line. That line is dead the second you draw it, okay? You can only do that once, and then if you want to change it, you got to change everything. Once again, we have a nice little line component, and now if I go back to the beginning of my script, what happens to the line? Ooh, I know, right? It's amazing, okay? So right away, we have 3 pieces of geometry, 2 of which are programmatic, okay? All of which are controlled by 2 things. this point, still the foundation of our design, and this slider. So as you can see, I can vary both those, and my whole definition changes. All right? This is key to understand. And everything, we're building this system that's all founded on variables that we choose. You'll sit down before and you'll decide them as the engineer or the designer that this is what needs to be done. We're going to find the midpoint of this line right now, as we've done. And this is all in the interest of, we know what our end game is. As we're scripting this, we know we need 3 points, a 3-point arc. So how do we do that? We need to have 3 points. This one's just the one that finds the point along the percentage of the way. And now it should be pretty simple to understand. What I'm going to do next is just find a 3-point arc component and type in my 3 points. Okay? But this next part is really to illustrate how easy it is. Like, if you do a spreadsheet, we've all done it. We have a bug in it. We don't realize it. We issue something. We screw up on our homework or something like that. We don't realize it because it's not very readily available to see if, oh, I put in the wrong number into this cell or something like that, because everything's hidden. What you'll see right now is I'm alerted in Grasshopper land by when something's orange, that something's wrong. Okay? But I'm also alerted by, I know what I'm doing. I know my end game is to have a 3-point arc. Okay? So it should come as no surprise that when I type in 3 points in a line, it's not showing me an arc. I don't need an error to tell me, hey, you screwed up something in your script, because it's right there. You didn't get what you wanted, and it doesn't quite make sense. You wanted an arc, not a line. So that's just to show you. I mean, we probably wouldn't make that mistake if we weren't trying to do a good example here, but that's to show you how the visual debugging aspect of Grasshopper will work over conventional programming media. Finally, here comes our last parameter. I told you, a point and 2 sliders. And this one, instead of going horizontally, is going to go vertically, and then we can have our nice arch. Get ready, because she's about to come. And there she is. And if we plug that one in now, there she is. So, can you guys all do oohs and ahs with me as we go through this parameters? I know you guys are shy tonight. Right? Ooh. Yeah, that's what I'm talking about. So as you can see, we had the 3 parameters that we knew from the get-go. We wanted something that could be easily moved and have its radius changed in 2 ways. We have that now, all right? So, you're saying to me right now, Medio, that's really fancy. Like, I like doing the oohs and ahs with you. And that's great. Batteries and spaghetti. What does that have to do with that complex building you were talking about before? I'll tell you. Everything we did was through this medium right here. Because that, what I just showed you, is the basis. That power is the basis of doing something much greater. When you get good at Grasshopper, I learn Grasshopper every day. It keeps getting better because it's such a deep program and you have so much you can do with it. So let's go through each one of the things that we had to do on this job for 2,500 connections, one at a time, and show you how Grasshopper helped us conquer that. And remember, one thing to keep in mind as we go through all that, no black box. Visualization is key. This is acting as an extension of my engineering mind. First things first, using Grasshopper to find the similar nodes. Remember, I can take my geometry over here that comes from the global building design. It has the layers on it that tell me what section sizes everything gets, and it tells me the geometry that I'm going to be playing with. I can reference that into my script just like we did the points in the 3-point arc example. This is the exact same thing. And now I'm going to feed it into a much more advanced script. And when you do that, it's going to be able to tell you exactly where your similar nodes are based on criteria that you choose, right? Visually. I'm not guessing. It's not telling me a number which I have to cross-reference somewhere else and then run and say, is this the right one? No. It's telling me that right away. And if I reference in new lines, it moves the points as you'll see right here. And this is key. That told you, like I said, this video is slightly sped up, but not so much that this didn't happen like that on this project. As you see, I have a bunch of different parameters here, not just sliders anymore, everything. And it's finding similar nodes for me. Now in the same way, we have visualized everything on this job. Everything is available to the engineer. Because remember what I said, it's all about extending your engineering mind. It's an extension of your hand. So what you see here is all the different parameters I have available to me. One of the key things engineers in the room will understand is if we do something like this, a local model that has forces mapped onto it. You're taking forces from a global model that are in equilibrium, and you're mapping them onto something else, which means that if you aren't in equilibrium in the second thing, you didn't do it correctly. So what's the first thing we do in the node design process? Well, we have this nice little panel here that tells us what the sum of the moments and forces are, because at the end of the day, we did the force mapping exercise in Grasshopper, because it has the vector tools that allows us to do that. And once it's in Grasshopper, remember, this isn't geometry, but it's visualization nevertheless, I can see right away before I even jump into an analysis world that I'm going to have at least the bare minimum successful analysis of being in equilibrium. Okay? But in the same way, look at all these different parameters I have here. And right now I'm showing what similar nodes are, but you say, well, how are you sure? I'm sure because I thought of this and I made a script to do everything for me to show me, hey, this is what I'm using. This is the criteria in which we're dealing with right now. This is why these are similar. Okay? There's no guesswork. The computer's basically telling me right now visually with my eyes that, hey, this is what I'm using. Is that okay? We're in control. We do not let this script handle everything for us. We did everything. It's a tool for us. Like I said, we're dealing with 57 million lines of data, and that's even worse than dealing with these lines. How do you determine if you're grabbing the right thing in 57 million lines of data? Here's a script that's showing us with our eyes in geometric space for all these similar nodes where it's grabbing the data for the force mapping exercise, which, as said before, is hard in its first place. But you know, if you're grabbing the wrong data, garbage in, garbage out, ain't no joke. All right? So just like that, I can pull up the gamma angles, I can pull up the node numbers, and you have no idea how much of a useful tool something like this is when you're trying to do even simple tasks. But when you're trying to do tasks like force mapping and complex analysis under a stringent program, you have no time to deal with not being able to do this perfectly. These are your local axes. These are the vectors you got to be dealing with. It's amazing to be able to pull up this screenshot and Midas at the same time and say, well, obviously we have a problem here. The vertical member has its axes off. We can fix that. We can spend 2 days trying to figure out what the problem was, or we can do it in 2 seconds and have it up on the screen and allow it to give us the power to see what's up. And once again, it's all about using your engineering mind. So we have tools right now that you're seeing. You're showing what forces we should be applying to the members, or what the computer thinks is right. But you get to come in here and do a final check and say, does that quite make sense? Is it really possible for all 3 of these to be in tension and then 1 in compression or something like that? That's what we're talking about. Pure visualization of millions and millions of lines of data. That's what's at your fingertips right now. So once you've found your similar nodes, now begins the nice process of finding all these constraints we talked about before. You have to find a node that will work with all those locations. Like we said before, it's not so easy, because we have this nice Saha envelope and we're dealing with extremely complex geometry in the middle. And in case you didn't hear it before, you're going to see it again right now. This is the middle portion of the building that we're selecting and going to isolate. And I think it's really important to realize that, you know, when you see this geometry, you know that your connection is going to stick outside of the bounds of the member, and that you're going to have certain problems because of that. But because you're sitting there and thinking about all this from the front of the things, you've already done all this, you say, okay, well, I need to be able to do fabrication and architectural constraints, okay? It's bonus points if you can get one connection detail that deals with something like this all over, okay? And that's where you sit down and you come up with something like what I'm about to show you, is the tin can. The tin can was the typical detail used in the freeform section, and it was born out of the 2 constraints that we talked about earlier, the fabrication and architectural constraints. Why fabrication? Well, first of all, any fabricator in the world can build a box like this, okay? It's not the hardest detail in the world. And that's something that we can send to him and say, please, Mr. Architect, or Mr. Fabricator, build. But how does it fit within the architectural envelope? I want you to take a good look at this fold line right here and the chamfer lines. It's a 2D curved envelope, but we certainly do not want to be specifying 2D curved plates. That's not easy to build. So you specify something like a chamfer line or a crank line, such that if the envelope were doing something like this, you essentially discretize the node to fit within it. So it's extremely flexible definition that instantly takes care of your 2 main constraints off the bat. And that's the cool part, because since it's a definition, since it's rule-based, we can define it in Grasshopper and save ourselves some time. So what you're seeing is right now, I have 2 lines. The crank shape, or no, the line shape, the outer can shape, and the crank line, okay? Just like I showed you before. These are the basis of our definition. Just like for the 3-point arc, it was a point, now we have 2 lines. And we have a whole lot of sliders, as you're about to see. But it's all within the interest of, how do I handle this problem quickly, one after the other, 400 times, okay? We have to be able to rapidly prototype this, because just because we have that definition doesn't mean we've actually met this specific node's criteria, okay? I reference those lines in, and right away you say, oh, Meteor, you created a can, good for you. But Zaha says, hey, why don't you turn on your envelope for me, will you there? See how I do that? I'm clashing with her envelope, and she's not happy. She's writing me an email, okay? The other thing is Mr. Contractor's calling me up and he's saying, geez, like, you really think I'm going to be able to deal with that kind of edge distance? Like, you need to think about fabrication tolerances and everything. Like, give me some edge distance, man. So I say, okay, who do I listen to? I listen to both of them. It's been set up in a way where we can listen to both of them. Watch me as I play with my one of many awesome sliders to bring up the lid. You say, Meteor, you're exacerbating that clash. Zaha's getting progressively more angry with you. But remember, we define this based on a crank line too. So watch as the crank line makes its appearance. Essentially right now what's happening is that with the lid. And it goes away. And in this way we know very quickly, we met both those constraints. Okay, everybody might not be completely happy, okay? Maybe he didn't get as much edge distance as he wants. But I've been able to prove very quickly that if you want it to be very, very easy to build, this is what we have to deal with right here, okay? And there we go. We know right away, hey, this is what the node's going to look like. This is the outer profile. Great. Let's say there was a clash. Remember, it all was based on 2 lines, right? Let's say there was a clash that I couldn't handle with my sliders. Well, I have this nice little line, and as you'll see here, it's basically just a nice piece of putty at this point that I get to massage into the architectural envelope and to do what I want with. All live updating. This is all pretty much the exact same speed you'd be doing it with your hands. Rapid prototyping was huge on this job. Being able to quickly come up with a design like this, unbelievable. Which is why some of these nodes, you're really able to get to the nitty-gritty of it very fast, because you're not dealing with, hey, am I in the envelope, am I not? You know right away from its conception that you are in the envelope. Just a little preview here of what's happening on site right now. I just got these site photos in today. That's what we just designed, for the record. That's how big it is. I want you to take a look. This is you standing there. That's about 10 feet away or something. Yeah, it's big stuff. This is what you're playing with the slider. This is where it ends up. Finite element analysis. For the engineers in the room, you're probably wondering, what's going on with this? How did you use Grasshopper for this? Well, it all comes back to using Grasshopper as a visual tool, but also utilizing the fact that Grasshopper isn't just visual scripting, it's visual basic scripting as well. So as you can see here, what I'm showing you is some of these components actually have visual code in it, proper code, not just visual scripting code. So essentially with that, you're able to link out to all these different softwares by what's called an OAPI, Open Application Interface. Just think of it this way, when you normally sit down to use a program, you're using its GUI, but with this, you're using it programmatically. And as you can see here, I have more definitions for geometry here. So this is more visual scripting, and it all ends up with me having a new connection. So now we're going to the flat side, right? So the flat side has this weird hexagonal connection. It connects 4 UCs in a SHS box. Beautiful, right? So there's your analytical geometry. How do you set up that model quickly so that you can get it done in 4 hours, Meteor? Well, what we did was we said, listen, we have to be able to expedite. We have to do this expediently. How do we do that? You use programmatic ways of inputting the data instead of the GUI, okay? So instead of trying to do this by hand like most people normally would, you use the OAPI, which comes with Robot. You reference it into your script over here with these tools that I'm using, and at that point, watch as I make my model here. See if I ever click over here other than to pan around. We won't. I guarantee you we won't, because at the end of the day, everything that you would do otherwise for a finite element model, look at them right here. Create the panels, create the bars, create the mesh. That's all been defined because we know we're going to have to do that for each one. Let's let a computer schlep it out, and then we can spend our time doing what we do best, designing, not these mundane tasks of setting up these models, all right? It also allows us more time to actually determine if these models are valid. I don't want to underscore how difficult these models are to make and to actually justify that they work. We, especially for the students in the room, finite element analysis is an amazing tool, but used incorrectly is extremely dangerous. So we got to be able to be on top of our game here on 2,500 connections. I don't want to underscore how hard it is even to get that mesh. In robot's got a terrific mesher on board, but if you give it crap geometry, it's not going to give you a mesh. And you could easily, and I have, spent a day trying to get something to mesh, but it's because you're doing it in the wrong way. You should be giving it clean, programmatic geometry, as we've been defining this whole presentation, right? Guys, my model's done. It's only 25% faster than what I would do in real life. All I have to do is press this button right here, and it's going to map the forces. And we're not going to do that right now because that's actually pretty boring. It's just numbers being thrown around between two softwares. But that's it. That's how we do it. And remember, all this was done in one medium. And just like Robot has an API, so does Excel. Everything so far has been based on you seeing things and you having data in front of you. We didn't stop there. Just because the connection's done, just because we have our nice stress plots and everything, it doesn't end there. And for the students in the room, I just want to stress this. When you get into the real world, you're expected to document your work. Legal reasons, engineering reasons, everything. You just expected to do it. But no one actually is going to be on top of you to make sure you do it. And sometimes you might be tempted to rush through it or do it, not so well because you're under pressure. And at the end of the day, you got the thing out the door, it's time to go home, it's beer 30, right? You don't want to do that because when you do that, you have condemned yourself to doing the work again. Because let's say your client calls you up and says, hey, Meteor, they want to have the member be something like this instead of that. Some minor change, or someone asks you, hey, is that really right? If you don't have something like this, which was created with the OAPI, just real quick, was sent over. If you don't have this, then you don't have anything and you have to do it again. And there's a huge amount of confusion and a lot of money at stake here. So that's why we did that, because now we take that time aspect out of it, just like everything else. The time goes out the window because now I press a button, it creates this nice thing for me, and I can't tell you how nice that is. Instead of scribbled hand calcs and something like that, a nice standardized template that says, hey, Meteor, this is what you were thinking at the time of the design. It can handle this, it can't handle this, blah, blah, blah. So don't forget that. This is all about visualization before, during, and after this connection design. And we're not out of the woods yet. We're certainly not, because remember, these bad boys right here, you need to be able to describe them to a fabricator who's up in China and he's cranking away at all these, and you need to be able to do that quickly for him. So what you're seeing here is me playing with more geometry. There's the crank lines and outlines for a lot of different connections, right? And you sit there and you say, how do you actually document all this? You have these crazy shapes, and like I said before, to actually do it on 2D drawings, typically, you would actually have to go in there and say, okay, I'm going to take a bunch of sections, I'm going to call it a bunch of points. It starts to get to be a real drafting nightmare. But on this job, we said there that it doesn't make sense either. Like, we're dealing in a 3D world, everybody's dealing in the 3D world. The contractor's using Tekla. So it doesn't make sense for us to make something in 3D, play with it, bring it down to 2D, give it to him, he plays around in 2D, brings it to 3D, only to bring it back to 2D for 2D shop drawings. I mean, it just seems like a lot of chances for error and a ton of time that we generally don't have on this job. So, like I said, after all said and done, I throw in the plate thicknesses from my analysis, and I have my 3D node right there out in space. I can see it. You can see right away, does it look right? Does this make sense? And then, what we agreed with the contractor was, what you guys saw before on the screen when I said, hey, like, this is the tin can definition, was the drawings for the tin can. And it shows the contractor, how do you weld this together, how does this work? But what it doesn't tell him is how to set out each specific one. How does he set out that specific one? We agreed with him, and you saw how quickly I did that, made that come up. We agreed with him that what we would do is we provide him that detail and then a 3D Rhino surface model of every connection on the job, such that he could right away look at it in the 3D space, bring it into his 3D space, and start working on it. No dealing with unnecessary 2D drawings. As you can see, I'm doing that again on the other side of the building here, just to show you how quick. Essentially, what I, or whoever is using this script over here right now is doing, they're doing the drafting for the job, and they're doing it immensely faster than the method that I previously described to you. And at the end of the day, what he gets is something that's pretty cool. He gets everything's on its own layer. So keep that in mind. We're going to show you a few just renderings now of when everything's on. And there's going to seemingly be member clashes. That's because not everything's supposed to be on at the same time. He can isolate things. He can check things, or we can check things right now. It doesn't clash, beautiful. And then I turn everything on. It's actually quite an impressive piece of work. And that's what we're going to show you right now, is just essentially all the different varieties of connections. Like I said, those members actually don't go into the connection. It's just a visual thing. But all the different types of connections that we had to deal with on this job. Different section sizes. And this is the full Monty. It didn't all get delivered like this. It got delivered in 5 floor or so batches to the contractor over the period of 9 months. And essentially, I think what it does is it just shows you this is what came out of Grasshopper. This was us using Grasshopper as a visual tool to be able to see these things in a preview space and then also take them to a drawing. It saved everybody an immense amount of time. And I think the one thing that I want to stress, that I have been stressing, is all this was possible because you had the right tool. We didn't give a computer a bunch of stuff and say, here, please spit this out, because a computer is inherently stupid. We are inherently smart, okay? And the computer would have never given us something like this. It would have never been able to work. Everything I did on this project, every other designer did on this project, was sitting there and saying, I'm thinking of something, I need a tool to help me do it. And that is what I hope you guys have taken away from this, is that this was a tool. It didn't drive the design, it was just an extension of our hands. So it's actually not just a nice pictures that I'm showing you in Rhino, it's actually going up, which is pretty impressive. So Dan's going to talk a little bit more about that.
So that was really fantastic. I mean, I've never introduced a TED Talk before, but that was great video. Incredibly impressive stuff. As Emilio said, without the software, there's no way we would have delivered this on time. Even with an army of people, if we had everyone in the office working on it, we wouldn't have delivered it in the same time frame. But it's reality. It wasn't an academic exercise. Emilio enjoyed using the software and doing great things with it, but it's happening on site. These are some of the images. We have someone in the audience who's actually the site engineer on this at the moment. So it's going up. The concrete cores are up at about level 23 or thereabouts. So that's going well. The exoskeleton's going up behind it. The fabricator's having lots of fun with this, fabricating it in China. The way we've given him the information and he's processed that and fabricated it has gone extremely well. So there've been minimum RFIs and it's all going well on site. And I quite like this image. It's not a great quality photograph, but it almost gives the impression that the exoskeleton is crawling up the concrete walls, the core walls, and making its way up there. Which reminds me of a film I often watch with my kids, Big Hero 6, and the microbots that build themselves into a building that looks remarkably similar to ours. So yeah, some other great photographs. The exoskeleton on the front, looking from the north side, so the grand height behind there, so it looks great. This is a visual mock-up of the facades, because that's not on site yet, or some of the facades are on site, but not a lot, but I wanted to show you how that looked as well. So this is an external and internal view of the facade. So this is a central section, the complex doubly curved areas, the exoskeleton, so it's a real exoskeleton. You can see the guys down here to give you the scale. It's enormous. And this is how it will look when you're inside the building, which is going to look fantastic, I think. So just to wrap up briefly, so what we didn't show there, but perhaps we should have, was the fact that obviously there's a lot of background, a lot of work that goes on before we start doing the scripting and generating the connections. So the solution has to be engineered first, and we built the connections in Rhino. We did some manually. There were some connections that were checked off in the finite element analysis even before we get into the programming world. So it's got to be engineered right first, otherwise you're just playing around with a nice toy and generated images, but to have it to work, and to work first time, and to deliver it in a tight time scale, then you've got to get the engineering right as well, obviously. Beg your pardon. Okay, and putting the complexity where it's best placed. So as I said, we simplified the structure as far as we could, so that when it came to the fabrication and the erection, then it was going to be smooth and it was going to go well. Breaking the complex problem into manageable parts. I think that you may have seen some of the scripts, the Grasshopper scripts and the spaghetti and batches, as Emilio calls them, but they tend to get lumped into small areas. So again, break it down into manageable parts. So you have a section that does one task, and another section does another task, and then you link them together with the spaghetti. But yeah, break it down. Grasshopper is a tool, you've got to get it all right, but it's a great tool providing you know how to use it and the engineering behind it is sound. And finally, as Emilio said a couple of times, if you want to learn Grasshopper, then you've just got to use it. There's a really good simple example that Emilio gave there with the arch. And I think that's a good place to start. If you want to use it, get Rhino, the software, download Grasshopper free, and just play around with it, play around with the sliders and do some oohs and ahs and have fun. And that's everything that we've prepared to tell you tonight. Quite a lot of information, I think more or less on time. Are there any questions from the floor?
I think it's a really, really impressive seminar talks here. Sorry, we run a bit out of time, so if you have any questions, you can feel free to ask both Emilio or Daniel outside the room, because somebody else is in the classroom now. Okay, so now we thank you very much for your seminar talk, and our chairman of HKISC is going to present you the souvenir